Swayam Prabha. Digital India. Educated India.
Dear students, welcome to next discussion on module of decision making. In this module, we are going to talk about terminal analysis. If you recall, in previous lecture, we looked into a problem where contractor has to take a decision based on certain experience or prior information that he already has, and then they have to decide whether to launch a crash program or not to launch a crash program. If you recall, I also mentioned that all the information is available, we have to treat it at its face value and then go for a decision whether to do something or not. However, sometimes what happens is that as things are progressing, as time is progressing, more data points get available, and you have to also account for that in your decision making process, and you may have to update your decision based on the new information that is available to you. When we were talking about fundamentals of probability and statistics, we learned that that is exactly where Bayesian approaches come into picture, that they give us a mathematical way to update the information, combine data with experience, and come with the posteriors or updated distributions of our priors, where sometimes we also call as priors as our beliefs. So, based on that, we are going to talk about terminal analysis. Here we will do one example on wastewater treatment process, where we did this particular example in our prior analysis as well. In addition to that, we will also look into our third example, where we are going to look into whether we should spend resources to acquire new data or not, because data collection is also an expensive process. So, how to decide whether we should go for data collection or not, and also we will revisit our site selection program as we go forward. So, as I already mentioned, that purpose of this particular topic is to understand how we can integrate additional information into decision making process, how we can reduce uncertainty and improve the decision outcome. Also, this particular approach is highly valuable in engineering, especially when we are trying innovative design concepts, because when these new design concepts are put into field, they go against the real world adversaries, and then you generate new data points. So, that this particular new data stream thus generated can be incorporated into our decision making, and this framework is only applicable when time is available to gather more data, because if you have to take a decision immediately and you do not have an option to wait and watch for new data streams to available, you would go with prior analysis. However, there is luxury of time involved, or you are doing certain projects in pilot mode, where you put them into in incubation stage, then you should definitely look into the hybrid of prior and terminal. One important thing to note, that when we talk about terminal analysis, that does not make prior analysis useless, or if we talk about strengths of prior analysis, that makes that does not make terminal analysis it's a secondary choice to go. It really depends what information is available, what is need of the problem, and what is the opportunity to update our answers, and based on that we as engineers make our best of the judgment which option to go for under different circumstances. So, when we talk about this additional information, of course, additional information, it does refine our decision making, and it is essential in complex or innovative projects that I already specified about, and this additional information is typically obtained either through research studies, through lab tests or field works, and all these three are resource intensive or thought intensive exercises. So, it has to be very well thought in advance whether we should be allocating resources to these three, what is the benefit in return to the engineering field or to the society or mankind or humanity by and large. But when we talk about these benefits, the costs are also involved. So, the costs of acquiring this new information is time, energy. I am not just talking about potential energy or kinetic energy in this particular case, but you may have to go in the field, sweat, get the data, come back and assimilate that into our decision making process. That is what we broadly talk about, the energy involved, and of course, financial resources, which is a huge commitment whenever we go on the data collection journeys. You might have heard about projects as big as expeditions, where a group of scientists would go on large scale expeditions, sailing through the oceans to collect this particular data and then come back to the field and pass it on to researchers and decision makers. So, it is a very well thought out and expensive process with lot of uncertainties involved, because you can be in wait and watch mode, that I will wait, when data will come I will update my decision, but sometimes it may happen that no new data stream is generated. So, there are risks involved to have a complete failed data collection process as well. So, those risks have to be also accounted for before we sign up for this exercise of terminal analysis. But if we have committed to spend time, energy and financial resources, we would expect some benefits out of that, and these benefits manifest in form of improved decision outcomes. Now, you will have higher confidence on the decisions that you would take after accounting for new information that is available. Uncertainty would be reduced. By reducing uncertainty, it does not necessarily mean that probabilities value will only go towards increase side. So, let us say that for certain possible outcome your probability is 0.5. 0.5 is a bad spot in probability world to be caught at in. However, if I can go on either side, that is, I can say that the probability of this process is now 0.1, that is only 10% chance that this something is going to happen. Even with reducing the probability, I have reduced the uncertainty here, because now there is 90% chance that this particular process is not going to happen. So, sometimes when we say that reducing uncertainty, students often assume that we are going to have higher values of probabilities associated. That is not always true, but it is going away from that 0.5 decision boundary, which is most confusing for the decision makers, what to do and what not to do. And however, whatever we do, this particular cost of time, energy and financial resources, it should be accounted for in some manner into our decision tree analysis, and that is what we are going to learn, how to account for that into that. Now, before we go into solving some numericals, as we always do, let us look into how this terminal analysis is going to impact our decision trees. There would be new information that would be added to decision trees. So, decision trees have to be modified accordingly. The decision trees have probabilities at its core, not the decisions, but the probabilities that help us choose one of these particular decisions. So, probabilities value would be revised. I am not saying it will always be revised. Sometimes the information that is available, it may not add any value to the prior probabilities you might have assigned. So, this word maybe is important. So, sometimes you will do an entire numerical or an exercise and you would see their answer is exactly same as prior analysis. You have not done anything fundamentally wrong, as long as your math is right. And but whenever we do this, it now reflects a more informed decision making process with improved accuracy of outcomes, and these are, like, broadly speaking, impact on decision tree. If you recall, whenever we were talking about updation of decision, we were talking about Bayes theorem. A quick recap, we used to say that probability of A given B is equal to probability of B given A into probability of A divided by probability of B. We also wrote about this particular relationship in the context of parameters, where we were saying that probability of some parameter theta given x is equal to probability of observing that particular x for a particular value of theta multiplied by prior probability of theta divided by probability of x. A quick recap: probability of theta in this case was prior, probability of x given theta was likelihood, and probability of x is called as marginal likelihood, whereas probability of theta given x is posterior. And idea of Bayes is that we start with some prior, we get the data, x is also called as evidence, and try to see that for a given value of theta, what are the chances of observing particular x or vector of x, and update theta accordingly. That maximizes that chances of observing particular theta for given x, and this entire premise we already discussed in earlier videos in Bayes theorem. And Bayes is an interesting and important pathway to integrate this new information into decision making. Whatever we were speaking earlier was broadly positioning need of terminal analysis, but the mathematical route to do that is through Bayes analysis, and every time refined analysis, updated decision trees means better decision outcomes with the given decisions. Again, I am re-emphasizing this particular point. We are not eliminating uncertainties, we are just updating those particular probabilities and have wherever possible reduced magnitude of uncertainty through this. So, if you recall, we did this wastewater treatment example using prior analysis, where we designed a wastewater treatment process and it was based on a completely new concept. Efficiencies of process was not known. Engineer had two choices: unit A, a smaller unit with higher efficiency; unit B, a larger unit designed for low efficiency, but we do not know efficiencies, we can only make a guess based on certain understanding, and engineer has to make a choice between A and B. So, I am introducing the notation EH for high efficiency, EL for low efficiency, what we actually observe, and engineers need to design based on this unknown efficiency level. We may know some probabilistic values for this, we can take some initial guess, what we also called as prior, and then try to take a decision on that. Again, a quick recap: what we recall is that engineer estimates, this is again a prior estimate because no experiment has been conducted yet. Based on the R&D team or technical team, they said that we believe that 70% chance that this particular process would have 70% efficiency to be high. If that 70% is actually true, then smaller unit with higher efficiency should work. However, if process is not as efficient than initially thought, you may need a larger unit to do water treatment for same quantity of water that is flowing. However, the cost implications are going to be different, that when we put a larger unit, it would be more expensive, and however, if efficiency is actually low, putting a smaller unit would cost us more money. If efficiencies are high and you put a smaller unit, you do not have to pay any overheads because all your assumptions fall in place. So, the costs are going to be at optimal level, that efficiency is high, you decided to go for a smaller unit, you do not have to pay anything out of pocket. However, efficiencies are low, you decided to put a smaller unit, what will happen in that particular case? You may not be compliant, you may not be able to meet the desired level of operations, as a result of which your costs will increase. On the other hand, you put a larger unit, there was a need of smaller one. Even if efficiency is high, you are going to pay out money. Even if efficiencies are low, you are going to maintain a larger unit now. So, that is why there is a confusion which particular design we should go for. And these are the situations where we used to make our decision trees. So, we will again make our decision tree. So, two decisions are possible, one is decision A and another is decision B. When we go with decision A, in real life it may happen that we actually end up seeing high efficiencies, what we assumed earlier, that is the only prior information available to us, or we can have low efficiencies, 30% chance of that happening. We can also go with B. Again, these efficiencies does not depend on our decision because they stem out from chance node, and EL is equal to 0.3. When we talk about relative costs here, if we go with this, we do not have to pay anything upfront. However, if we go for smaller unit, this is small and B is large, we may have to shell out 100 units extra. So, this is with minus sign, because you made a completely wrong choice. A smaller unit when efficiency is actually low, not a good place to be in. When you go with, let us say, larger design, it is given to us that the cost that we have to pay is minus 50, and in this case we have to pay something around minus 20. In that case, if I do the math, expected cost given that I go with A is 0.7 multiplied by 0 minus 100 multiplied by 0.3, this comes out to be minus 30. In second case, minus 50 into 0.7 minus 20 into 0.3, this number comes out to be minus 41. And it is very clear that based on this particular decision tree, I have to pay less money while going for A. I will choose A as the optimal decision based on this information available. Now, not B, but we will choose the smaller unit A. Now, this site engineer is not comfortable that what if I install a smaller unit and efficiency indeed turns out to be on the 30% chance, then the entire non-compliance issues are going to come into picture. What should I do? Now, there are two options, either go by the what we call as gut feeling and say I will build larger plant, but then over long period of time you are paying 10 units, 10,000 multiplied by 10, some few lakhs or few crore rupees extra, just because you did not have confidence in the prior analysis. So, whenever money is involved, we cannot typically go with our gut feeling that do this, we will end up saving money and so on. So, you have to take an informed decision. So, what are the options? Next option that scientist or engineer will explore is that let us set up an experiment and do some tests and really determine whether efficiency is actually high, actually low, or what it is, so that we get an updated probability. 70% is a guess. If I can go to 80%, 90% or close to 1, that is always better for decision making process. So, what engineer will do? They will go to a research lab, they will go to some testing lab and say that, hey, we have designed a particular unit, can you please tell us whether our process is energy efficient or not. So, engineering and then the testing lab would also have their own uncertainties involved, because it is very difficult to have a perfect information available, because all the experiment simulations we do, they have their inherent uncertainties involved. So, lab will share their prior experiences that we have done similar testing and our accuracy is 80%. That is, if you actually give us an efficiency which actually is high, there is 80% chance we would label it as high rated, we will give it a high rating. However, we still have 20% errors in our experimental processes, in our models that we use, and the cost there is MR, that we instead of saying that it is high and low, we will give you 3 ratings: high, medium and low. So, when your process is actually high, we may say that we will say that it has high rating with 80% confidence or 80% chances. 15% chances may also happen that we may classify it as a medium range, and only 5% chance we will classify actual high efficiency process as a poor, and the chance of that happening is 5%. Again symmetry does not apply on the other side. So, if efficiency is actually low, there is only 10% chance we will say it as a high rated process, 70% times we will actually classify it as a low rated, and 20% chance we will be somewhere between high to low, and we will call it as a medium rated process. And this will take money. This is what our terms and conditions are. Do not expect our answers to be absolutely free from uncertainty. We will only help you update probabilities from 0.7 to whatever based on these particular values, but whenever you will give the samples of or the specimen of your machinery, we will charge you money. And they said that the upfront cost that we are going to charge is something around $10,000 that you may have to pay. It does not matter what is the outcome. So, what we will now do is that we will try to summarize all these information that is available to us. Cost of test is $10,000 or something around 10 units. This could be anything. This is what testing agency is charging. It is up to us that whether we will go with this decision or not. So, now whatever was given to us, you can think of it, this entire story as conditional probabilities being made available to us. That is probability of HR given process is actually EH is 0.8. Probability of MR given EH 0.15 and so on. So, whatever information was available, I have translated it into terms of conditional probabilities, and I will be doing this Bayesian using this particular conditional probabilities. So, our goal is to find the best decision choice A or B, but before we do that we have to first decide whether we should go and conduct the test or not, and to do that we will try to make our decision tree. So, here are some key derivations that are involved that we may have to again go back and look into that how to incorporate Bayesian here. So, what is given to us? Let us write it down. We know probability of EH, what we were also calling as prior. This is known to us. Prior is given to be 70%. Initial belief is there, 70% chances it is a high efficiency process. So, testing agency cannot discard it fully. It has to account for that input that is coming from the engineer or R&D team. Another thing that is given to us is probability of HR given EH that testing agency has specified, given that it is actually a high efficiency process, we will rate it high, is given out to be 0.8. This is not a perfect information from the testing agency. Perfect information would have probability equal to 1, no errors involved. However, it is practically impossible to get access to perfect information more often than not, and hence this represents more of a realistic setup. Then we have to update this 0.7 to something better, because this is the source of confusion. Engineer does not have full faith on this 0.7, they want something more confidence on this 0.7, that is why the testing comes into picture. What is the way to update? We will say that let us update this EH given results. Let us say the first possibility is that result is actually high. So, using Bayesian we can write it as HR given EH into probability of EH divided by probability of HR. Now, if we talk about probability of HR, this is unconditional probability, what we also called as marginal. That is, even if actually it is high efficiency, you can still label it HR. If it is low efficiency, you can still label it as HR. So, it would be probability of HR given that process is actually EH and what are the prior associated with it to be EH, plus probability that it is labeled as HR, but it is actually a low efficiency process multiplied by what are the chances it is a low efficiency process. This is the total probability also. We already know these particular numbers, that probability of HR given EH is 0.8, probability of having EH is 0.7 based on our prior analysis, plus probability of HR given EL is there are 10% chance to commit that particular mistake, and probability of EL is given to be 0.3, and this number should come out to be 0.59. So, this becomes denominator of our Bayesian. It is easy to do here, but in real world Bayesian inference is very tricky because it is very difficult to determine the marginal likelihoods, and lot of approaches come into picture. But here we are lucky that in this case we can work out this particular number much easily. And then if we have to incorporate this number, we already know that probability of HR given EH was 0.8, this particular guess was given as 0.7. We get the updated probability of EH given that test outcome was indeed labeled as HR to be 0.8 into 0.7 divided by 0.59. Now, it is very clear that probabilities are always less than equal to 1. You are dividing by a number which is smaller than 1. So, Bayesian would always give you an update. If denominator what could happen is that if numerator tends to 0, your probabilities would shift leftward from 0.5. However, if your numerator also has a considerable value and you divide it by a number less than 1, it would shift rightward. So, you would go away from that 0.5 zone, and that is exactly what Bayesian help us do that in terms of reducing the uncertainty associated with the particular process. In this case, this comes out to be 0.95. You can check that calculation for yourself. So, what was our prior belief that there is only 70% chance that this particular test, this particular technology is going to have high efficiency? Given that agency rates it high, you have now 95% confidence in your prior. You are paying money to reduce that uncertainty from 0.7, that is 70% to 95%. So, uncertainty there was 30%, now your uncertainty in term loosely speaking has been reduced to 5%, that 95% sure this is going to be a high efficiency process, and then you can go ahead with the smaller unit with much higher confidence. In physical world nothing has changed, it is the same unit A, same unit B, only thing that has changed is your confidence in decision making process. As of now we have not gone to the agency, these are all conditional likelihoods. Given that agency rates it high, what is the updated probability? Agency can also give it a medium rating when you send the samples for testing. Agency can give it as a lower rating when you go for the testing. So, we have to also count for that, but to first close this argument, if EH given HR is equal to 0.95, we obviously know that probability of EL given HR is also equal to 0.1 because everything should sum to 1, 0.05 because everything should sum to 1. So, 0.95 plus 0.05 should give you number equal to 1. If this is clear, we will shrink this, we will shrink this and put somewhere in the corner and continue our discussions further. So, I will just take it and put it here for our references. In similar fashion, you can work out another number of probability of EH given it is rated MR and probability of EH of EL given it is rated MR, which would be nothing but 1 minus what we would get above. I am not going to repeat all the steps for you here, but I can tell you that this number would come out to be 0.637 and this second number would come out to be 0.363. Now, you see initially you were 70% confidence, your prior was 70%. Now, testing agency has given you answer somewhere in the middle, your confusion has further increased, that they are also not able to classify whether it is a high efficiency process or a low efficiency process. Now, based on that particular outcome, you have more confusion now. So, this is one classic example where Bayesian does not guarantee that your probabilities will actually get inflated or deflated. So, you have to actually do the calculation to reach that particular conclusion whether it is helping or not, but this actually tells us that now you have to go back to your R&D team, do more testing, more fundamental analysis and come with the clearer answer. You should not just go with that your prior belief, because now you are more confused. From 70% you are now confident only 63% based on that particular outcome. Similarly, probability that it would be rated EH given its probability of updated belief that it is a high efficiency process given lab has rated it as EL would be 14%, around 0.143, and probability that it is given that company rating is LR and it is actually a low efficiency process is 0.857. So, you can be 85% confident that this is a bad process if rating agency also rates it bad. So, all the probabilities have been updated now. Now, let us make the decision tree. Now, if you see here that we have to take two decisions now, one I am circling in red box here and red box here. One decision is that whether we should go for testing or we should not go for testing. Now, when we do not go for testing, the choice are that we go with our prior analysis, go with A and B and go with the same probabilities that we assumed earlier of 70% and 30% of having EH as 0.7, EL as 0.7. In that case, if we go with A and EH, the cost that we have to pay extra is 0. When we go with A, EL, the cost that we have to pay is minus 100. Similarly, if we go for B, the cost for EH is minus 50 and EL is minus 20 as we noted earlier. So, this does not change anything for us. Even the costs that we are going to calculate here, they are going to be 0.3 into minus 100, which would come out to be minus 30. In second case, we would calculate it to be minus 41, and in that case, of course, if we do not go for test, our decision is going to be A star based on the no testing scenario. However, if we go for testing, what may happen is that we may get an output of an HR, we may get an output of MR, we may get an output of LR. If you recall, from the denominator of our prior analysis, we got this probability as 0.59, we got chance of observing MR as 0.165 and chances of observing LR as 0.245, which has to be accounted in decision making. But let us say that we get an output of HR, then there are two options. In fact, this should be a decision node, that we take a decision from here whether we want to go for A or we want to go for B. If we go for A, and this should be again a chance node, because these three things are associated with probabilities. So, you go for test, you take a chance with three probabilities of HR, MR and LR, and because these you do not know that whether you are going to get HR or MR or LR, all these are probabilistic outcomes. Given that output is HR, you will decide between A and B. Given that output is MR, you would decide between A and B and so on. So, this is a decision node again. So, again going back here, if you get A and B, instead of using 0.7 as probabilities, now you will use 0.9 probability and 0.05 probability, because your prior has been updated to a new value. If you go with A and efficiency is actually EH now, on which you have 95% quote unquote confidence, still you have to pay for the testing cost. Minus 10 is the expense that you are going to definitely incur. If you go with EL, and now there are 5% chance that you go with the smaller unit and efficiency comes out to be lower, but the penalty now is minus 100 minus 10, which is 110 units for cost. Similarly, for B, cost would be up by 10, from minus 50 it would be minus 60, from minus 20 it would be minus 30. Similarly, if outcome is MR, you go with A, and since MR has put you in a more confused spot, you would see that your prior from 0.7 goes to 0.637 and it goes to 0.363 when you get an output of MR and EL. All these numbers you may work out using exactly similar method that we followed, that is, it is just solving the the Bayesian, that what is the probability of EH given MR, it would be probability of MR given EH multiplied by probability of EH divided by probability of MR, and this all the numbers are exactly worked out in a similar fashion as we worked out when we were updating the probability of EH given the output was HR. So, this is again a repetitive calculation that you have to do. Going to the last case, when your test results are indicating LR, in that case you see that your chances of actually having a low efficiency is now 85.7%. What you were thinking as 30% has been updated to 87%. So, the other side remains 14.3%, and when you plug in all these particular numbers, your decision tree is now branched into 4 different branches, one shown in blue, one shown in green, one shown in purple and one in yellow, each indicating that what is the possibility, and then you account for that into your decision making. So, now next organic question arises is that what is the value of this information? How much should I be paying for this particular information, that am I saving more than 10 units? Because if you are just saving 5 units by spending 10 units of money, then this particular information is not worth it. But you have to quantify that how much money are you indeed going to save when you go for this additional information, and we call this as VOI or value of information. If value of information is greater than test expenses, your test is economically justifiable. That you say that I went to this lab, they give me a report and I was able to save 50 units by paying them 10, your net profit comes out to be 40. So, that particular information was indeed valuable. On the other hand, if you end up saving, as I said, 5 units by spending 10, then the information you obtained is not necessarily valuable. Using this particular decision tree, you can actually end up deciding whether I should pay for that particular test or not, and we will look into that using this particular decision tree itself, that whether it was worth it or not. So, expected cost, when you went for no testing, it came out to be minus 30 in one case and minus 41. This was associated with A and this was associated with B. So, even when you decide not to go for testing, you would never go and construct B. Why? Because the costs are higher upfront. So, in that case your A star is going to be the actual decision. So, this is the only cost that you would be worried out post decision, that I am going with A because it costs 30. However, when you talk about test, expected cost given that you go for test is essentially there is 59% chance that your outcome is going to be HR multiplied by whatever is the best or optimal decision that you have taken out of A and B, multiplied by its cost. You will not just multiply it by cost of both A and B, because you have taken a decision either this or that. So, you cannot add the costs across the decision boxes, because all of them are not intersecting with each other. So, you would decide whether I am going with A or I am going with B. In this case, it was pretty clear that we are going to go with A because size is smaller, efficiency is higher with 95% confidence, and that number would turn out to be minus 15, because if we just quickly look into the math from our table, minus 0.95 multiplied by 10 plus 0.05 multiplied by minus 110, and the number would actually come out to be minus 15 units that you would pay if you go with A star in that particular case. In this case also optimal would come out to be A star. In this case, both of them are actually going to be give you the same cost. All I am doing is multiplying this probability by the cost, adding them together for all these branches separately and finding which is giving me the lesser cost. So, in this case it would be minus 0.59 minus 15. In second case it is 0.165 into 46.3, and in third case it is minus 0.245 multiplied by 34.3, and at the end it comes out to be minus 24.86. Now, this includes the cost of testing, by the way, because this is coming from the decision tree. Now, if I have to calculate value of information, I cannot double count the cost of test. I have accounted for cost of test. Without testing, this decision would cost me minus 14.86, because everywhere I have added an factor of 10, it would get discounted, and sum of probabilities is going to be 1 anyway. So, 10 is appearing as one single 10 unit of the cost, and without decision, without the testing, I am going to incur the cost of 30 units. If I go by my definition, that cost of test minus cost of no test, where I am excluding while calculating VOI, I does not include the cost of testing in C test. Otherwise, I would end up double counting it. So, this value of information in this case comes out to be 15.14 units. And how much I have paid for the test? I have paid 10 units for the test, and the value of this particular information is 15.14, and it ends up saving me 5.14 additional units of money or benefits even when testing is done. So, in this particular case, the difference between the expected cost with test and without test is so large that going for the extra information is worth it, and I should be paying 10 units. However, if agency would have decided to charge me 20 units instead of 10 units, in that case this particular number would be this particular value would be less, come into the negative sign. That would mean that I should not be paying for particular test, because I am giving up more money than saving. So, I can go without test and go with the particular probabilities, as the value or expected losses are going to be higher if I go for testing inclusive of testing costs, as a result of which I make much more informed decision. All right, let us move to next bit more complicated example, where we bring in the probability distributions into picture and try to see whether our decisions will change or not with new information being available. In this question, we again have two sites, sites A and site B. We already did this particular example when we were doing prior analysis on earthquake. This is exactly the same problem, where we also tried different types of cost functions, but now we will build on that and see that if new information is available, how we are going to add it to our existing decision making framework. So, cost benefit analysis shows that if we go and make our dam at site A, we will be reaping benefits of 22 units. This 22 could be million, billion, that does not matter, all these units are consistent. If we go for construction at site B, we are going to reap in 20 units of benefits. However, the problem is both of these sites are susceptible to earthquakes. So, benefits should not be the only thing guiding our site selection. We have to account for the seismic parameters at both of these locations, which is also include the risk component in our decision making. So, we did some seismic study. This was assigned to, let us say, 2 labs. One lab said that at site A, different models give us different parameters, and at site A we get 2 parameters that expect 0.01 or on an average 1 earthquake in 100 years. At site 2 expect 2 earthquake in 100 years, roughly speaking. Again, I am not saying these in deterministic sense that 1 earthquake will come in 100 years. These are just parameters of a distribution. We will call these as parameter nu or lambda, because I am going to use Poisson processes. So, we will have to use these as parameters of that particular distribution. Similarly, at site B, these parameters are given as 0.005 and 0.01. Sometimes we are tempted to see that the values of parameters are 1/2 at site B. So, the probability of earthquake happening, x number of earthquake happening is also 1/2. That is not correct, because the probability distribution function or mass function itself is a nonlinear function. So, just by halving the parameters does not necessarily half the probabilities in 1 by 2. One thing is for sure that probability of having x number of earthquakes at B is going to be lower than A. How much lower, that we have to identify or find out by doing the math around whatever distribution that has been given to us. One more condition is given to us, that after each earthquake this dam will be repaired and restored to its original condition. So, let us say that the 50 year is the design life. If 5 earthquake happens, you have to pay the cost 5 times, or if 10 earthquake happens, you have to pay the cost 10 times to repair and restore it to particular function, the intended function of the dam. So, design life is given to us to be 50 years. It is important in the context of Poisson because parameter is per year, and we will convert that into 50 year or design life. So, every parameter would be multiplied by 0.01 into 50 to get the net parameter during its operational life. Also, cost function is a linear function here, L is equal to 5x, and we calculated the expected loss for both the sides here, but just for a quick recap, we will quickly write the math of it for both these sides. One thing is given to us is that loss is equal to 5 times x. Expected value of loss at site A for 2 parameters can now be worked out to be x equal to 0 to infinity x 5x into px. Why? Because expected loss is probability of having particular x, and x can be, we can have theoretically 0 earthquakes to infinite earthquakes, and we have to assign the probabilities through our px probability function. In this particular case, I can take constant out. So, this becomes x equal to 0 to infinity x px. I am lucky that it is coming out to be x px summed from 0 to infinity, which is nothing but expected value of x itself. If x comes from the Poisson process, the expected value of the PDF or PMF in this particular case is same as parameter itself. So, it becomes 5, design life is 50 multiplied by the original value of parameter per year, because I am writing 50 separately here. So, it becomes 250 times mu j. This applies to both site A as well as B, by the way, because I have not plugged in the values of parameters just yet. So, now I can say that expected loss at site A is, there is 50% chance that this particular parameter takes value of 0.01 multiplied by 250, plus there is 50% chance that this particular parameter takes the value of 0.02 again multiplied by 250. So, this number would come out to be some 3.75 million. Similarly, expected loss at B would be 0.5 multiplied by 0.02 into 250, not 02, 0.005 first, 0.005 into 250 plus 0.5, 0.01 into 250, and this number comes out to be 1.875 million. Now, net benefit from A at A would be total gains minus expected losses, and similarly net which and this number comes out to be 18.25. I already did the math, but you can do it just subtracting 22 from 3.75. Similarly, net benefit at B comes out to be 18.125. So, still despite these losses to be higher at A, I can still go for A, because the net benefit 22 minus 3.75 is not able to offset the net benefits at B. So, the best decision in absence of any other information still remains to be A, that I will go with site selection A in this particular case. However, an interesting phenomena happened that we got 20 years to observe this particular sites and one earthquake of damaging intensity occurred at site A. On the other hand, site B in last 20 years recorded no earthquake. Now, the stakeholders came back to us, said that new information is available. Before building the dam, would you like to change your decision? So, one question arises here is that would this historical data would provide insights about seismic risk at each stage, or in other words, should I adjust my prior assumptions at each of these particular locations and try to see whether my probabilities should change or not. Now, what I will do here, I will try to update that what is the probability that VA would remain to be 0.01, given that one earthquake has happened and this was x equal to 1 in 20 years. If you recall that we were assigning same probability to both the parameters when we were doing our original analysis. However, now with new information, we may have to update the confidence we have in each parameter rather than going with 50% weightage to the two parameters. We have an opportunity to update these particular parameters. So, how we will do that? We will do is what we will do here is that we will again use the Bayes theorem to write it in other way. We say that this is probability of x equal to 1 in 20 years given VA is equal to 0.01 into probability of VA is equal to 0.01 divided by marginal, which is probability of x equal to 1 in 20 years. What I will do here, I will say that when probability of x equal to 1 in 20 years, when VA is equal to 0.01 is nothing, but it is e raised to power minus lambda, lambda to the power x upon x factorial from the Poisson distribution itself. In this case, e raised to power minus 0.01 into 20, lambda in this case is 0.01 into 20 raised to power 1 divided by 1 factorial. What was my initial belief? It was 0.50. What is my denominator in this particular case? I have to basically look into probability of x equal to 1 given VA is equal to 0.01 multiplied by probability of VA is equal to 0.01 plus probability of x equal to 1 given VA is equal to 0.0. What was the second probability given to us? 50% chance, it is 0.02 multiplied by probability of 0.02. Because these were the only two parameters that were known to us, I was assigning them some weights. So, while calculating the marginal likelihood, I try to account for total probability irrespective of the value of that what are the what specific value this parameter is taking, but it is dependent upon that whether VA is equal to 0.01 or equal to 0.02. Right now, I am doing this in a discrete domain. I can also do it in a continuous domain and account for all possible values of parameters, but here my objective is to reassign the weights of 50% to these particular parameters after updation of information, and this number should come out to be around 0.378. I am again not simplifying the math because all these values are known. We already did this particular part that I am highlighting now in the numerator. If you change the value of parameter, the only number you have to change is that instead of 0.01 you use 0.02. 20 comes from that in last 20 years this particular data is available. So, your probability gets revised to 0.378. Then what is the probability? Updated probability that VA is equal to 0.02 with availability of this new information, it is 1 minus 0.378. So, something around 63% or 0.63. See, what we were betting equally on two probabilities. Now, the weight has shifted towards higher parameter that has more susceptibility to produce larger number of earthquakes. So, instead of using 0.5, I should be using a new probability values of 0.63 and 0.3 for the two parameter values. Now, another question arises, sometimes we would say that okay, now we have done that, let us end the question here because no earthquake has happened at site B, but there is another information that is hidden there, that no earthquake has happened in last 20 years. So, x equal to 0 in 20 years is also an information, because 20 years you observed no earthquake. So, more weightage should be given to lesser parameter now, because no earthquake happened at that particular location. So, rather than giving same probabilities to lower parameter and higher parameter, now more probability should be assigned to low chances of earthquake, because nothing happened in 20 years. So, what we will do is that similarly for site B, we will calculate what is the probability, that parameter value at site B. If we go to our original problem, we were given these probabilities as 0.005. So, it is 0.005 given x equal to 0 in 20 years. We can again follow the same Bayesian approach and say that what is probability of x equal to 0 in 20 given parameter value of 0.005 multiplied by probability of 0.005 divided by probability of x equal to 0 in 20. Again we will follow the same math, e raised to power minus lambda, lambda to the power x upon x factorial into 0.05, because this was our prior and Bayesian does include the term of prior with 0.5 divided by e raised to power minus lambda, lambda to the power x, x factorial into 0.5. Here I will use lambda 1, lambda 1, lambda 1, because denominator would have another parameter lambda 2 over which I am doing entire summation. We will write these values shortly. So, lambda 2 raised to power x upon x factorial into 0.5. This is a general formulation. In this case x equal to 0, lambda 1 is equal to 0.005 multiplied by 20. This multiply by 20 is important because this is the data obtained in last 20 years and rate is per year. So, per year multiplied by number of years is the actual parameter in Poisson, and lambda 2 similarly is 0.01 into 20. We plug in these particular values, we should get some updated answer, and that should, and here you can see that values may not shift drastically in comparison to previous case. In previous case we moved from 63%, from 50% to 63%. In this case perhaps this particular shift may be from 50 you may move to 48 and other probability may move to 52, but I will leave it to the audience to do this particular calculation and find the values of probability of 0.005, and once you do that, updated probability of 0.01 given x equal to 0 in 20 years would be simply 1 minus whatever is the probability you calculated above, because these are the only two possibilities of parameters that we have been discussing so far. And now you have updated parameter only, and what we were doing here exactly remains same, but with instead of using probability of 0.5, we now update our probabilities with 0.63, 0.37, 0.52 and 0.48 whatever we get. But in nutshell what we have been able to achieve, we have been able to account for recently available information for which we waited for 20 years into our framework and update our decision. And when you solve this particular decision tree, which again I would leave it to you because you have to follow exactly same steps, but with revised probabilities, you would see that the decision now changes from site A to site B because of the additional savings that you are encountering. With that we will end up our discussion on terminal analysis and conclude the discussions on decision trees in our next lecture. Thank you.